Okay, so let's keep going on this. Are there any questions about the actual proof of ATM being undecidable? Let's actually go through the proof again because I'm sure you guys want to get a better idea of how the proof goes. Okay, so let's go back through. So the proof is to show that ATM does not have a decider at all. So there's no machine that will be guaranteed to always halt on all inputs and get the correct answer. That's what undecidable means. So what we did is, suppose that a machine did exist that decides it, gets the right answer, and always halts. Then, by that reasoning, if we want to prove the undecidable statement, we must have something wrong happen with regard to H. Because if nothing goes wrong, then we can't claim undecidable. But if we get a contradiction with regard to H, therefore H's existence is not true anymore. So therefore there can't exist a decider because we're just assuming one exists. We looked at what does a decider actually mean? It means you say accept or you say reject always, you never run forever, and you get the right answer. So if it's the answer really is accept, you better get the right condition. And then reject is precisely the opposite condition. So in this case, it says accept if the machine it's given accepts the input to that machine, and it says reject in any other case. So it says reject if it outright rejects W, or it just runs forever on W. So we're just assuming H knows how to do that process, whatever it is. Then what we do is we'd say, oh, let's just build a machine. Because we can't just rely on H like this, because it could very well that some technique exists that is general that allows us to decide ATM. What we need is another machine to actually get us a contradiction. So we build this machine which takes a single Turing machine as input, and we have H, this supposed decider for ATM, be run on M with its own source code. So we're allowed to do that because the source code of M is just a string. We need to provide a machine and a string, and we provided both those. We're allowed to do that. It may not make sense to do that, but we're allowed to do that. That's the key. And then the second step of D, just do the opposite of whatever H said. If H said accept, we say reject. And if H rejects, we say accept. We're allowed to do that. It might not make sense, but the key is we're allowed to do that. And we reason that since H is a decider, then D must also be a decider for whatever language it is. We're not interested in what the language of D is because we'll show it doesn't exist. But we're just building a machine here. So the only way we can build this machine D here is if we can build H. Because if we can't build H, we can't build this machine D. Fair enough. So we saw D as a decider. We looked at what does it mean for D to be a decider. It takes a single machine again, and it says accept or it says reject. If it says accept, because the machine did the opposite of what H said to do, then it says accept if the original machine does not accept its source code, because it does the opposite. And it says reject if it does the opposite, if it accepts its own source code. Well, because D is a decider, it must get the input right on all possible Turing machines, including itself. So what if we fed D its own source code as its input? Well, just substitute the M for D here. So D says accept on its source code if it does not accept its own source code, which is a contradiction. It rejects its own source code if it accepts its own source code, which is again a contradiction. So therefore, D cannot possibly be a decider because it gets the input wrong on at least one input. It gets the answer wrong on at least one input. But the only way we were able to build D is if H existed. So therefore, D cannot exist, which means that H cannot exist. Okay? And because H cannot exist, there can't possibly be a decider for ATM, which means it's undecidable. Any questions about that? You won't prove something like this on the final. I guarantee that. That it's just for you to think about, well, we can have machines that disagree with themselves. So it turns out, and we'll get to this eventually, a lot of the interesting properties of Turing machines that we may want to know, we can't actually solve. There's no algorithm at all to solve them. So like an example would be, suppose I wanted to know whether in an introductory programming class, we have a sample submission that does something, and we take student submissions of their programs. And we want to make sure whether or not they have the same language, meaning they do the same thing. Well, what we'll show is that there is no algorithm to do that in the general case, which is actually quite interesting. Yeah, so we'll get to that eventually. But any questions about this? Okay, so let's actually prove one more thing. So let's look at this. So we'll prove the following theorem, that a language L is decidable if and only if L is recognizable and L bar, the complement of L, is also recognizable. Okay, so what this says is that you can actually get an algorithm for a language if you know how to recognize the language itself and recognize the complement of that language. They can be two totally separate machines, but you can build an algorithm from those two machines. Isn't that kind of cool? So what this would imply is that if ATM, the complement of ATM, was recognizable, then ATM would be decidable. Because we showed earlier, let's go back up here, we showed that ATM is recognizable. So if we somehow showed that ATM bar is recognizable, then by this, then ATM is decidable, which it isn't. So how would you actually prove something like this? If you see an if and only if, how would you prove something like that? You can do contradiction both ways, but the main idea is that one implies the other. That's usually how you go here. Another way you can go is A implies B, and let's see, what would it be? It would be A bar implies B bar. So if A implies B and not A implies not B, then I think that would do the same thing. But what we're doing here is A implies B and B implies A, which is logically the same. Okay, so let's do the easy direction first, which is if L is decidable, then can we get a recognizer for L and its complement? Well, let's see. If L is decidable, is it recognizable? Ignore the L bar part. Is the language itself recognizable if it is decidable? Yeah, so that's something we've seen before. So L decidable already implies L recognizable. I'm actually going to shorten recognizable to REC because I don't want to write it out over and over. Okay, well, how do we show that the complement is recognizable?
So the complement would be just...
Well, we'll get to that. So if L is decidable, what if L bar were decidable too? Well, if L bar were decidable, what would that imply about L bar? The complement of L. If L bar is decidable, what does that imply about being recognizable? It's also recognizable by the same reasoning. Because that's just the definition again. So what we would need to show then is that if L is decidable, then its complement is too. So what is that usually called here? If a set of languages, you apply an operation and you still stay in that same set of languages, what is that called? Closed under complement. So it suffices to show decidable languages are closed under complement. So are they? Think about what decidable means. It means you always will say accept or reject, and you can never run forever. Well, think about the Turing machine itself. Well, if you said accept, what state did you go to? Q accept. What about if you said reject, what state do you go to? Q reject. What if I swap those two states? Well, is now getting the complement, but because it was a decider, I still halt on all strings because I didn't change anything else. So what we can do is swap Q accept and Q reject for the Turing machine for L to get a decider for L bar. Sweet. And the answer is correct because there's no other states other than Q accept and Q reject where you could ever say accept or reject. So just swapping them is totally okay here. Cool. So therefore, if L is decidable, then its complement is decidable too. And the two statements we had up here get us the decidable implies recognizable condition. Any questions about that? Okay, so now we got to show the other condition. So the first one was just mainly an application of the definition and then one closure property. So here is something that's a little harder but not too bad. We're given two different recognizers, so they do not have to halt on all strings, okay? Remember that. We're given two recognizers, and we want to build a machine that doesn't halt, that always halts, okay? We're given two machines that might not halt, and we want to make a machine that always halts. Shoot. Well, here's an idea that won't work, so tell me why this doesn't work. Well, what we can do is say, well, whatever string that we're given, one of the two machines will say yes. It's either an L or it isn't. So because it's a recognizer, one of the two machines will stop eventually, right? Because they're guaranteed to halt on the strings in their languages. So what you can do is say, I'm going to feed the string to the machine for L. If it says accept, great, it's in the language. If it doesn't say accept, then we feed it into the recognizer for L bar. And if it accepts, then it's not in the language, so we say reject. And otherwise, we say accept, because it would be in the language in that case. Don't worry about the details. Think about, I feed it to one machine, figure out what to do, then I feed it to the other machine, figure out what to do. What's wrong with that idea for recognizers?
They can go forever.
They can go forever. That seems like an issue because they're just recognizers. They may not halt. So what could we do? Any ideas? Well, let's think about it. Is one of those two machines guaranteed to halt at some point? Yeah, because whatever string we pick is in one of the two, so therefore one of the two machines will halt and say whatever the answer is. Both of them might actually halt, but at least one of them halts. Well, could we try a lockstep idea? Start both machines and then try one step, and then try 2 steps, and then try 3 steps, and then try 4 steps. Will we ever stop with one of the machines at some point? Yeah, one of the machines will stop at some point. Well, could it be the string be in L and in L bar simultaneously? No. So once one machine stops, I don't care about the other machine. Pretty cool. So this is what is called simulating in parallel. We're not really doing it in parallel. We'll do one step of one machine at each point, but we're guaranteed to never run forever because one of the two machines must stop at some point. So here's what we do. So to get a decider for L, remember, we have to have the machine always stop no matter what. So here's what we do. So on input W, because L is an arbitrary language, it might not encode a machine. It's just a string in this case. So we don't know, and also we don't know how many steps we need to go until one of the machines says yes or no. So let's just do a while true loop, and then at some point, once one of the machines makes a determination, then we'll break out and then figure out what to do. So while true, then we'll have a step A. So run so run the recognizer for L for one more step on W. And B is exactly the same thing, but for L bar, for one more step on W. Well, it could be that the recognizer for L, that recognizer says yes or something. Well, one of the two machines will say accept at some point. We don't really care about the reject case because one of the two will say accept. So if the one for L, not L bar, says accept, well, the one for L says accept, therefore the string is in L, which means we need to say accept too. Because we're building a decider for L. We need to agree with the recognizer for L. But in the other case, if the one for L bar says accept, meaning that the string lives in the complement of L, what should we say for the decider for the language itself, not the complement? Reject, exactly. So we should say reject here. And that's the whole machine. So we're just lockstepping the machine in parallel, one step at a time. It's like the robot dance, I guess. Until one of them is guaranteed to say yes. If it's the one for the language itself, then it's in there. If it's the one for the complement, then it's not in the language we want to build a decider for, so we need to say reject in that case. And we're guaranteed to be a decider here because at some point one of the two machines will say accept because they're recognizers. Any questions on how that actually worked? Yeah. It could be the other machine keeps running if the first one said halt and let's just say accept. If one machine said halt and accept, the other one it can't say accept at some point because it's the complement language. But it could reject or run forever. We don't know in general because it's just an arbitrary recognizer. It may or may not halt at all, but we're making it run one step at a time. We're not having it run to full completion, which is why we can actually guarantee that this will actually stop at some point. If I said, oh, run the recognizer entirely on W, then it might not halt, and then we could have an issue there. But by doing it one step at a time for each one of them, then we're guaranteed to halt.
What if the one says reject and the other one, the other machine doesn't has the answer?
Good point. So let's just say the recognizer for L will say reject at some point, and let's just say it does say reject right now. And then, therefore, L bar should say accept because it's the complement. It lives in there. Remember, recognizers have to halt on the strings and say yes on the strings in their language, which means that the recognizer for L bar eventually must say accept at some point because the string is in its language, because the one for L said, no, it's not there. So one of the two must say accept at some point. We don't really care about the reject because the other one must say accept at some point. Yeah, we don't care because the other one will say accept at some point.
You can't run the machine for the next step.
No, that's why I have the while true thing. So we run it from one more step. If neither of the two said accept here, we go back and then try again for one more step. And then just keep going until one of the two machines says accept. Other questions? Yeah.
Okay, so let me just clarify.
Yeah,
So because there's a language and there's a complement, if you have a string that's running forever, because it's not in the language, the other one should have it?
Yeah, because the one for the, so you're saying the recognizer for L runs forever,
Yeah.
For example. Then the one for L bar, because it's recognizing the complement, the string is in that language by
Because
definition.
it's not in the other one.
Right.
It should.
It needs to be in that one. But because it's a recognizer, it needs to hold on those strings, which means it will accept at some point.
And the other question is, what's the arrow? I couldn't.
What arrow?
The arrows.
The left here. It's, I guess it's notation. It means that, look at the if and only if thing. The arrow going to the right, I guess, means the thing on the left implies the thing on the right of the if and only if. And then the one going left means the thing on the right implies the thing on the left. It's notation I'm used to. Are you guys not used to that notation? What are they teaching you in 243? My goodness. It's gotten worse since I took it 7 years ago.
When I took it, my professor wasn't there for 3 weeks.
Oh, well. Yeah. It's one of the reasons why I'm going to another university where the computer science department takes care of that class instead of offloading it to the math department. So
Innovation level is
yeah,
lower.
yeah. And 243 is not standardized. We've tried to make it standardized in the CS department, but no one in the CS department wants to teach it. So we're stuck with the world that we're in here. Oh well. Any questions on this proof, though? Enough slander. It's not really slander, but any questions on the proof? Okay, so let's see. What are the two things we showed about ATM, the language ATM? It's undecidable, but what was the other one? It's recognizable. Oh, well, what does this theorem tell us then about the complement of ATM?
It's not recognized.
It's not recognizable.
Because it's not the same.
ATM bar is not recognizable. Because if it were, then we already know it is recognizable. And the previous result tells us that we can get a decider out of it, but we know that one cannot exist. This is really interesting because now we finally have a language that is recognizable but not decidable, and a language that is not even recognizable. So that, what does that even tell us? You can't actually build a Turing machine for this language at all. Isn't that weird? And have it halt on the strings in this language. You need to guarantee that. There's no Turing machine to do that. There's no computer program to do that. Isn't that weird? I think that's pretty weird. Okay, any questions about how we actually got that? Okay, well, what was the set of languages we talked about? The A languages, we did the ADFA, AENFA, whatever. What was the one we did after? The empty version. So let's do the empty version for Turing machines. So ETM is pretty much what you would expect. It's a set of Turing machines where the Turing machine does not accept anything. Nothing surprising. What do you think this language is? Decidable or not? Oh, come on, you have a 50-50 shot. So we have some say decidable, how many say un? It's like a tie. It's undecidable. A little tip here, pretty much everything we're going to prove with Turing machines is undecidable. Not everything, pretty much everything though. And there's going to be a general result called Bryce's theorem that we're going to prove, which allows us to pretty much get a lot of undecidable results really easily. So what we're going to actually do here is use something called Bryce's theorem, which is basically a giant framework to prove things undecidable. We're going to do the quote-unquote brute force way here. So there are really two ways we can show undecidable results. The way that we're about to do it, and Bryce's theorem, which is far easier, but you can't apply it everywhere. And we'll get to that eventually. This technique will always work. So we want to show that this thing is undecidable. So we could, although I'm sure you probably don't want to do this, and I don't either, to go through a similar type proof with ATM, but with ETM instead. Do you think you want to do that? Hell no, I don't want to do that. It's 9:10, I don't want to do that. Let's do a much easier proof. Well, what was the idea behind the ATM proof anyway? Well, what we did was we supposed that H was this decider, then we made a decider, this D machine that's also a decider that couldn't exist. Let's do a similar idea, but with ATM instead. Let's actually suppose that ETM is actually decidable. This claim is wrong. Then, using that assumption, let's build a decider for ATM, which we know cannot exist. It's the same idea. Okay, so let's actually prove this. Suppose that, and I'm going to call the supposed decider E. Yeah, let's do E. Decides this language ETM. And trust me, this proof will be a lot easier than the ATM one. It's basically like the big hump to get to the really easy part. The ATM was the big hump. This, from now on, is going to be smooth sailing down the mountain. Okay, so for that reason, let's actually try to build a supposed decider for ATM. So let's try to decide ATM. So what does ATM take as input again? Or a decider for it, I guess. So it takes, if you remember, a machine and an input. where M is a Turing machine and W a string. So remember, we're trying to build a decider, supposedly, for ATM, not ETM. We suppose that ETM does have a decider, but we gotta use that decider in some non-trivial way to get us a decider for ATM. Okay, so how in the world are we gonna do that? Well, we can't just run M on W again because it might run forever, because it's just an arbitrary Turing machine. So what can we do? And furthermore, we gotta use the ETM machine somehow. And what does the ETM machine take? It takes just a machine only, no input. So whatever machine I feed into this supposed decider E, I can't have any input attached to it. It better be just the machine itself. Well, I can't feed, let's just say that I feed the input Turing machine, the M that I'm given, into this decider E. And suppose that we determine that the language of this machine M is not empty at all. Does that tell me anything about whether M accepts W? If it comes back and says, oh, the language of M is not empty, it accepts something, does that tell us anything about whether M accepts W? No. So, on the other hand, if it says it is empty, that does tell us something. But we kind of want a more comprehensive solution here. So, the way that we're going to do these undecidable proofs from now on is we're going to build a machine and then use that machine fed into this decider E. So, we're going to build a machine as our first step, and then feed it into this supposed decider E, and then let E figure out whether that thing has empty language or not. So here's what we're going to do. We're going to construct a Turing machine. Let's call it Z. So one thing that you should keep in mind here is that this machine, all we're doing with it is just building it. We're not running it. If we are going to run this machine, it could run forever, but we're not actually running it, okay? So we're just building it. So this machine is going to take some arbitrary input X. It's just a string, that's all that it is. And what is Z going to do? The first step of Z is to run M on W. And you go, huh? Why would you do that? Remember, I'm not running M on W here. We're not doing any simulation. I'm just building the machine. I'm taking this machine and input and building it into the source code of Z, directly into it. Well, here's what we're going to do. If M accepts W, then accept X. So what in the world are we doing here? So what we're doing is just building this machine that does something behavior, that does some behavior depending on whether M accepts W or not. So think about it. Let's think about this for a second. So when I start up this decider, which I take the M and W, the machine M and the input W for it, and I'm about to start making this Turing machine Z. So I'm already given the M and W thing. Is the answer of whether M is going to accept W going to ever change once I start building the machine? No. Wait a second. So if the answer never changes, let's say that M does accept W. Well, what does Z do? Well, it says on any input at all, run the machine, and the answer is going to always be the same because we just run M on W. Well, the answer of m, if m is going to accept x, that's always going to be true. Well, what happens? We accept the string x that the machine z has. So if m accepts w, what is the language of z? Does it ever not accept anything? No, because it'll always pass the test if m accepts w. If m really does accept w. So let's see. So if m accepts w, then z accepts everything. Because if m accepts w, the answer of whether that is true or not will never change, because I never modify m or w at any point. So the b step will always succeed in this case, which means I will always accept x. So no matter what input z is given, I will always accept it in this case. Any questions why that's true? Remember, we're just building the machine. We're not running it. Well, let's see. The other case is if m does not accept w, then, well, let's see. If m really never accepts w, then the b step will never succeed because it never accepts it, and the answer doesn't change. So will I ever accept the x string? Because the if test never passes. And so therefore, I will never accept the input that z gets. So what is the language of z? Does it ever accept anything? No, because the if test never passed. So that must mean that z does not accept anything. So why are we doing this? We're trying to make this machine have two different behaviors. It has one behavior that we want and the other behavior that we don't want. The behavior that we do want corresponds to saying accept, I guess the opposite, never mind. So we have two behaviors. One corresponds to m accepting w, the thing that we're given, and the other one corresponds to m not accepting w. Remember, we're just building the machine, we're not running it. But that must mean that if m does not accept w, the language of z is empty. And if m accepts w, the language of z is not empty, namely everything. So what does that mean? If we feed this Turing machine z to the decider for emptiness, then if it tells us, yeah, it was empty, then we know whether m accepts w or not. Because that's exactly what the Turing machine says to do. So that's what we're going to do next. Feed z into e. I guess that's not that formal, but we're running the supposed decider for emptiness on the machine that we just made. So therefore, because the E machine, the one that says empty, it's a decider. So if E accepts, well, let's see. Let's go back. If the emptiness test said, yeah, your language is empty, well, what does that tell us about the language of Z here? It's empty. Well, did we ever accept anything if the language is empty? No, we didn't accept anything. So did the M accept W test pass or fail? It failed. So if I want to figure out whether M accepts W, should I say yes, it did, or no, it didn't? No, it didn't. Come on, it's a coin flip at this point. Uh, so let's go back again. We're in the case of the Z machine does not accept anything. Yeah, because the emptiness test said, yeah, it is empty. Well, if we look back at our two cases right here, there are only two cases. That Z does have empty language or it doesn't. So the one that corresponds to it being empty is when M does not accept W, because that's how we built the machine Z. Well, that must mean that M does not accept W. Well, I'm trying to decide whether it does, and we just figured out it doesn't, so therefore we should say reject, because we're essentially doing the opposite here. So this is not the only way to do this, build this supposed decider. You could do the exact opposite, and then you could have the same answer at the end. There are many ways you can go, but this is one way you can do it. And then, of course, if E rejects, then we should accept, because it corresponds to the other case. So what did we do? We built a machine, fed it into a supposed decider, and inverted the answer. So does this, well, this gets us the language that we want for sure, because that's how we actually built the machine. It either had empty language or it didn't. So, and we were able then to figure out whether M accepts W, because the answer is the opposite of whatever the emptiness test said. Well, the only thing that we want to check is this actually a supposed decider for ATM? Does this really decide ATM? Because if it doesn't, then it doesn't tell us anything about whether ETM is decidable. But if it is deciding ATM here, then this supposed decider for ETM cannot exist. Because if it did, then we can make a decider for it. So we just need to check, does this run in a finite amount of time? Well, what about step 3? Let's go backwards. Does step 3 run in a finite amount of time? Yeah, it's just inverting the answer. What about step 2? What is E? A supposed decider. It must always halt. Cool. Step 2 runs in a finite amount of time. What about step 1? Are we ever running Z directly? No. So does it cost me infinite amount of time to write out the source code of a Turing machine? Not to run it, just to write the source code. No, it takes me a finite amount of time to do that. So step 1 takes a finite amount of time too. Cool. So therefore, ATM is decidable, right? What do we know about ATM? It costs a lot of money. It's undecidable. But ATM is undecidable. So ETM also is undecidable. Okay? Yeah, go ahead.
Here, ATM is undecidable because you got it wrong.
No. This really would be a decider for ATM if this supposed decider existed. So, what is a good way of thinking about this? This decider exists implies ATM is decidable. So the contrapositive says, if ATM is undecidable, then this decider can't exist, because it's logically the same thing. And so, because we know ATM is undecidable, therefore our decider supposedly cannot exist. Other question?
So in order to use that ATM is undecidable, we would have to prove that ATM is undecidable?
Yeah, we needed an undecidable language to start with in order to get other ones. Yes, so that's the main reason why we suffered through the ATM proof. But now these proofs are at least a little bit easier because you can think about what you're actually doing here. So what is the key? The key is this step 1 right here. The key is we're building a machine that does one of 2 possibilities depending on what the problem we're trying to solve is. The problem we're trying to solve is the ATM problem because we're trying to build a decider for it. So we have 2 different behaviors of this machine. One that so they differentiate whether or not M accepts W. One of them has M accept W as one case, and then the other case is that it doesn't. Let's do one more next time, unless there's a question.
Can we say that ETM is undecidable since ATM immediately without the whole group?
Well, you need to be able to show that one implies the other.
You're gonna make this
Possibly.
possibly.
There's a much easier method of proof that we'll get to eventually.